In this lecture, we're going to step through a dynamic analysis, specifically focusing on the example that was provided in the notes. And so when we talk about a dynamic analysis, of course, this is one that will involve acceleration. So we're dealing with with a system in motion. Now, whether we're talking about a static analysis or a dynamic analysis, really our overall goal is to solve for all of the unknown variables once we have identified all the variables in the equation. So the importance of following the prescribed method that we introduced with static analyses and continued that with dynamic analyses is that oftentimes the unknown variable won't be obvious at front. Oftentimes the unknown variable will begin to be revealed as we start to step through the prescribed approach. And so our example here is a person performing an elbow flexion maneuver. They're lifting a particular weight. However, in our example, we are going to ignore the weight. And so we're just going to pretend that the person's performing elbow flexion without holding anything in the hand. And this arrow indicates the direction of the movement, the presumed direction of the movement. Now, when we begin to perform the dynamic analysis of this task, we first need to collect some helpful information. And the first piece of information that we need to start to gather is anthropometric data. These are data that will describe the structure and the basic properties of the system of interest, which is the forearm and the hand. Now, we start with the fact that the forearm and hand has mass, and that mass is 2 kilograms. The length of the forearm and hand in our problem is 34 centimeters, that we have to convert, of course, to meters. The center of mass is located 68.2% of the distance from the elbow towards the end of the segment. And we obtained this value from Dempster's table. Now, what I've done here on the front end is I've gone ahead and calculated the actual value in distance units. So when we talk about the 68.2% obtained from Dempster's tables, this is a unitless measure of distance. This is a relative measure. What we need for the dynamic analysis is the absolute length in terms of meters. And so we take the full length of 0.34 meters, multiply it by the 0.682 value, and we arrive at a value of 23 centimeters or 0.23 meters from the elbow towards the end of the segment as to where the center of mass is located. Because this is a dynamic analysis and we know that it will involve the moment of inertia, because this is a rotating segment, we need a measure that will allow us to calculate the moment of inertia. And so I'm going to use the radius of gyration from the elbow, not the center of mass, because I want to calculate the moment of inertia directly without going through the parallel axis theorem. If I wish to do that, then I need the radius of gyration value of 0.827 from Dempster's table. So these are data that characterizes the system of interest in terms of its structure and its inherent properties. Now, we also need information regarding the conditions in which this system, the forearm and hand, is operating. And so one of the conditions here is that the biceps muscle is exerting a force of 675 newtons. Now note that this sits in contrast to some of the previous problems we worked where the muscle force was the unknown variable. And so in the problem statement, I haven't made any reference to what we know and what we don't know, particularly what the unknown variables are. So we have a biceps force of 675 newtons. The anatomical insertion of the biceps is located 2 centimeters, okay, so very close to the joint, and it inserts at an angle of 81 degrees from the negative horizon, negative x-axis with respect to the point of insertion. The final condition here is that the motion of the forearm and hand is captured to have an angular velocity of 1.3 radians per second. And so if you encounter data in degrees per second, those data must be converted to radians per second. Now, it's also important to note that the dynamic analysis in this situation is going to be limited to the forearm and hand in the horizontal position as it transitions through that horizontal position. So this is not a static situation. The arm is actually moving into the flexion direction, but we captured a single snapshot of the system at when that forearm and hand is perfectly horizontal. So we have our prescribed method that we follow to a T here. So we need our coordinate system, and we're going to use our XY system. Now, the XY system, as explained previously, is a system of convenience for reference, and that's going to be particularly convenient for us because we're isolating our examination of the moving arm captured when it hits that horizontal position as it transitions from the extended position into a flexed position. And because the forearm is perfectly horizontal, it aligns perfectly with our x-axis. We also then, once we have our coordinate system, we're then prepared to move on to our free body diagram. And now we have to add a kinetic diagram because this is a dynamic situation. And once we have completed our two diagrams, we then transfer our variables in our diagram to our equations of motion. And that will be the procedure that we'll follow here in this lecture. So we'll start with the free body diagram here on the left. And because the forearm and hand inherently has mass, we represent the mass through the weight of the forearm and hand. And we always represent that with a vector, always oriented perfectly vertical and pointing towards the object to which it is attracted to, and that is the Earth. Now here I've gone ahead and calculated the weight of the forearm and hand by multiplying the mass times the acceleration due to gravity, the 2 kilograms times 9.81 meters per second squared. So this is always going to be something that you have to be aware of. Now, the problem indicated that the biceps muscle force has a magnitude of 675 newtons, and it is angled from the horizon at 81 degrees. And notice here, it's very close to the axis of rotation here in the elbow, but it does have a physical separation. Now, when we see the system here, we know that this is a rotating system, but the system is not able to experience pure translation horizontally or vertically. And the reason that this forearm and hand cannot experience pure translation in any direction is because those motions are constrained. Those motions are constrained by a reaction force acting at the joint. So the reaction force is being generated by nature of the anatomical construction of the elbow joint. Now, in terms of the magnitude and direction of the FR, which is the reaction force, we don't have information provided in the problem for that reaction force. What we do know is that it does exist, but what we start with an initial guess as to the magnitude and direction. So the direction that I have it drawn here is just a habit that I use whenever I draw these. I always just tend to to draw these vectors at this angle, as you can see here, but if you drew it at a different angle, that would be just as fine, so long as you ensure that you provide a label for it. And for consistency purposes, we'll stick with the FR representing the reactionary forces taking place at the point of the external contact of the system, and those reactionary forces are in response to the biceps force and the weight of the forearm. And one final variable that we also have to be aware of that will describe the direction of that reaction force, of course, is the theta of that reaction force, the angle from the horizon. Okay, so now that we have our free body diagram computed, we're then prepared to start with examining Newton's second law. And that is that the sum of all these forces on the left-hand side of the equation, when we add up all of these forces, they're going to be equal to the mass of the system of interest, the forearm and hand, times the linear acceleration that system is experiencing. Because we're dealing with a rotating system, we now have to include the angular counterpart to Newton's second law, such that the forces that will compel the rotation, forces that have non-zero moment arms, will contribute to the moments of force influencing the kinematic behavior of the system of interest. So we have to go through and collect up all of our forces that have non-zero moment arms. That will populate the left-hand side of this equation. And when we add up all of those moments of force, they will equal the inherent resistance to a change in the angular motion of the system of interest, the forearm and hand. That inherent resistance to a change in angular motion is captured by and described by the moment of inertia, I, which we'll describe a little bit later. And that's going to be multiplied by the angular acceleration that the system is experiencing in this situation. Okay, so by dividing these equations in half, centered at the equal sign, we've taken care of the left-hand side. Now we have to address the kinematic behavior on the right-hand side by drawing a kinetic diagram. So we start with a vector. Now this vector is not a force vector. Vectors, remember, are directed line segments that represents a magnitude and direction of some quantity. Forces aren't the only quantity represented by vectors. Acceleration are vector quantities, and the acceleration in y is going to be a scalar multiple of the value of mass, and that's going to be acting vertically because we have previously defined everything we do must be expressed with respect to x and y. We also have a horizontal directed vector, but I'll come back to this in a moment. We also have a rotation vector. Now, vectors are always linear, but this is a representation of a vector. That vector is our angular acceleration vector, and that's going to be a scalar multiple of the moment of inertia, as I mentioned, we'll address a little bit later. The horizontal vector here that you see is the horizontal linear acceleration as a scalar multiple of the mass. Now, by focusing on AX and AY, we've seen this before. Horizontal accelerations, at least a horizontal acceleration because the arm is in a horizontal position here, AX, can also be expressed as the R, the length, times the angular velocity squared. That's our centripetal acceleration, the tendency of the system to accelerate towards the joint. Now, keep in mind here, this is acting at the center of mass, so R in our equation is not going to be represented by the full length of the segment, but rather the location of the center of mass from the joint. Moving on to AY, we've seen this before. AY is at, in this case, a right angle to the position of the arm, which is horizontal, and that vector is tangential to that circular path, and that's going to be equal to the location from the axis of rotation of the elbow to the center of mass in R times the angular acceleration. One last point to make here is that when we go to our free body diagram, we see our biceps force and our reaction force are not abiding by our frame of reference. So although I don't have this detailed on the diagram, what we will have to do is we'll have to take this biceps force vector and break it up into its y component and its very small x component. Likewise, we'll have to do the same thing for the reaction force at the joint. We will have to resolve it into its x component and its y component. Now, before we continue with our dynamic analysis, on this slide I want to speak a little bit about external contacts, because that's going to give us some important context and perspective with respect to the systems that we're analyzing. In this lecture, the system we're analyzing is the forearm and hand rotating about the elbow. So on the bottom right-hand corner of the slide, here we see a model which is basically a simplified representation of the forearm and hand. It could be a representation of the lower leg, the thigh, upper arm, so on and so forth. And so here we have the segment that represents the forearm and the hand. Very simple model here that has mass concentrated at a center of mass, and so therefore the weight is represented as our vector, as we've seen before. Now the triangle is, we've discussed the triangle as a fulcrum. This is the external contact. We have it in dotted because we don't typically represent external contacts in the free body diagram. I like to include it because it does give us some perspective to the overall system we're trying to model here. So now, because of the nature of this hinge joint, so when you see the triangle, that suggests to us that we're dealing with a hinge type of joint. This external contact will prevent the system of interest, the rigid bar, from experiencing pure translation vertically, okay, pure translation vertically, and pure translation horizontally. It does so because of the nature of the connection between these two pieces right here. Now, the reason it can prevent those types of pure translations is because the external contact will restrict that by applying a reactionary force in the y direction, and it will apply a reactionary force in the x direction as well. Now, we're going to contrast this with the same system of interest, the rigid bar. Instead of pinning it in a hinge joint, we're going to bury it into a surface. And so this is a symbol you've seen before, rotated 90 degrees. So this dotted symbol represents a surface. In this case, it's not the ground, it's a wall. And so what we've done with our system of interest, our rigid bar, is we've taken that bar and we've buried it into the wall rather than resting against the wall. And so in doing so, this bar still has weight, it still has mass, and that weight's represented with this vector. But the external contact here, the external contact will constrain the motion. It will prevent this bar from experiencing pure translation vertically, pure translation horizontally, because it's capable of generating reactionary forces. But what the third type of motion that the wall to which this bar has been cemented into will also prevent this bar from rotating. And it does so by exerting a moment of force. So where our model on the bottom right hand corner of the slide is a simplified model of a joint, this is typical of a balcony in apartment buildings. And so the balcony materials certainly have a weight. people are standing on this balcony, but the balcony is static. It doesn't move. It doesn't move because the wall and other external fasteners that are connected to the rigid bar that serves as the balcony prevents linear motions, and it prevents it from rotating. So the W here, the weight of the balcony itself, has a physical separation from the area of contact. Therefore, it's capable of generating a moment of force and would cause the bar to actually rotate. But we don't want that in balconies. Therefore, the external fasteners and or the wall in which it's cemented into will be able to generate a reactionary moment of force to counteract the weight of the balcony itself and however many people are standing on that balcony. Okay, so as we move back to our dynamic analysis, we take the approach by starting with our equations of motion in the x direction. So what we want to do here, I'm going to ask you to pause the video in a moment, and what I'd like you to do is to go back to the free body diagram and the kinetic diagram. Specifically for the free body diagram, you're going to go through and find all of your force vectors in the x direction, populate the left-hand side, and you're going to find all the relevant terms for the right-hand side, specifically for those accelerations in the x direction. And then once you've populated those with the labels, complete the next step of substituting the values that we've been provided, compute a final solution, and then restart the video, and we'll see where you are. Okay, welcome back. Presumably you've attempted it and you've restarted the video. So I've gone to my free body diagram, and I found that I have a force of the reaction in the x direction, and the way I initially guessed was that the reaction force of the x component was in the positive direction, but the anatomical characteristics of the biceps muscle and its connection is such that the x component is pointing in the negative direction. So at this point in the next step, I decided to indicate the direction as well as the labels, and that's going to be equal to mass times ax, because that was the only x-directed variable in the kinetic diagram. Now, when we look at these variables, we find that we can expand them. And so the x component of the biceps force, we keep it as a negative, but we can express it as a function of the resultant magnitude of the biceps force, which was given to us, times the cosine of the insertion angle. And that's going to be equal to, of course, the mass of the system of interest times the centripetal acceleration, which is the distance from the elbow to the center of mass. Okay, that's our R value, times the angular velocity squared. So now we find our values that on slide number 1, and we substitute those values for the variables that we have. And so we have 675 in the resultant force times the cosine of the insertion angle, and we have the mass of 2 kilograms, the distance to the center of mass from the elbow of 0.23 meters, and the given angular velocity of 1.3 radians per second. Make sure you square this term first before multiplying it by the 0.23 and the 2, and you quickly realize that we only have one variable left standing. And what we find here is that we have a final value for FRX of 106.4 newtons, and because it's a positive value, my initial guess of the reaction force in the x direction was correct, and it's pointing in the positive x direction. Now we move on to the y direction. So as we did on slide number 4, pause the video and go through and collect all of your variables from your free body diagram and your kinetic diagram, populate the equation, expand, substitute the values that you have, and then derive a final solution. Okay, once again, welcome back. And I'm going to go through and collect up all of my variables. And so I have f, r, y. That was my initial guess. Okay, so I guessed that the y component would be in the positive direction. The biceps component in the y direction. The y didn't is sort of merged with the s here, but this is the y component of the biceps force. That's acting in the positive direction because that's anatomically determined. Subtract the weight of the arm, and that's going to be equal to the mass times the tangential acceleration, which is the y direction. It's in the y direction. It's also the tangential because the forearm is perfectly horizontal. So that's r times alpha. We expand the y component to be a function of the resultant force magnitude for the biceps times the sine of the insertion angle. Subtract the mass of the forearm times the acceleration due to gravity. Nothing's changed on the right hand side. So now we go ahead and substitute the values that we are given, or values that we can possibly even calculate at this point. So we have 675 newtons times the sine of the insertion angle. Subtract the mass of the arm and forearm and hand, 2 kilograms times 9.81 meters per second squared. As we saw in previous lectures, because I worked in the direction of the weight in my initial statement, I don't have to add, in fact I shouldn't add a negative 9.81. The negative is already taken care of and accounted for in the fact that the overall quantity here is acting in the negative direction. And that's going to be equal to 2 kilograms times 0.23 meters for r. Once again, we're going from the elbow to the center of mass. And we go through our calculations. It's my habit to do these calculations, figure out the products one at a time. I like to do things step by step, keeps me organized. And then what I find is I have a final expression with alpha and FRY. I have two unknown variables. I have one equation. So if you think that, well, on slide number 4, I had another equation, remember we computed a final value for FRX. There was no unknown left in that equation. And the reason it doesn't necessarily help us is because on the backdrop, we don't know the angle for the reaction force. Remember, theta has to still be determined. And so what we really do have here is really just one equation and two unknowns, leaving us stuck. However, the good news is we still have a third equation because we're dealing with a rotating system. And we have the sum of the moments of force is equal to the moment of inertia times the angular acceleration. So what you want to do here, I jumped the gun a little bit, but pause the video, collect up all of your forces that have non-zero moment arms, and you have to collect up the forces that are expressed in x and or y, and then couple that with the kinematic term on the right hand side from your kinetic diagram. Okay, welcome back once again. And so when I go through my free body diagram, I find that the only force coming close to the joint that has a non-zero moment arm is the y component of the biceps muscle. And so that happens to be the insertion point of the biceps at a right angle from the y component. And so that's actually 2 centimeters from the joint. I'm going to subtract that from the weight of the arm times just simply the distance to the center of mass from the elbow because it's in a horizontal position. So that's going to be helpful in that regard. I have I elbow times alpha. Now, although we aren't explicitly given alpha, we're not explicitly given the value for the moment of inertia. Alpha is still our unknown. We can compute the moment of inertia before moving on to the next step, and that's what I'm going to do on the lower part of the slide. So calculating the moment of inertia about the elbow, as I mentioned, I'm going to do this directly rather than going through the parallel axis theorem approach, and that's going to be equal to mass of the rotating segment times the radius of gyration from the point of rotation, which is the elbow, not the center of mass, squared. So I find I have 2 kilograms from Dempster's table. I indicated the value on slide number 1. I have 0.827, but 0.827 is a unitless value. We need the radius of gyration in distance units, and that distance unit is the full length of the forearm and hand at 34 centimeters, or 0.34 meters. So in terms of calculating the moment of inertia, because the radius of gyration is done directly from the point of rotation being the elbow, we have to take into consideration the full length of the segment. And working through our calculations, we have a moment of inertia of 0.158 kilogram meters squared. So as we move back up to our equation, we substitute our variables for the numbers that we have. We have the 667 newtons we computed earlier, the insertion point from the joint center, 2 centimeters, 0.02 meters. We have the weight, the distance to the center of mass, what we just calculated for the moment of inertia. And before moving forward, we just take a quick glance and we find that we only have one unknown variable, and that's great news. So just continuing with my habit of computing the products first, take it to the next step, and then complete my mathematical calculations. And what I find is a final value for angular acceleration at 55.9 radians per second squared. And it's important to note here that the radian is a unitless variable, and we need to have a unitless variable to balance these equations. So now that we have a value for alpha, we can now back substitute in the y direction equations that we had on the previous step, slide number 5. We were left with a situation where we had 2 unknowns. So by moving to the next equation, we calculated a value for alpha. We're now able to go back, substitute that value for alpha, and then now we've rendered our first problem now to be one that we can solve, because we only have one last variable, one last unknown variable. So working through the math, we find a value for F, the reaction force in the y direction, to be negative 621.7 newtons. Now recall my initial guess, because I didn't have any knowledge of what that magnitude was going to be, nor its direction, my initial guess was that the y component for the reaction force was in the positive y direction. But the fact that a negative value came up indicates that my initial guess was wrong. So I have to go through and change my free body diagram to reflect the fact that the y reaction force is actually pointing in the negative direction. And that's what this symbol represents. So given that, this is the quick fix, this is the quick correction to it. So we just use this vector to represent the true direction of it. If you had calculated a negative value and you have to change it, that's perfectly fine. You would get full credit for it. If you had initially guessed that it was in the negative direction, you would not get a negative value here. It would be positive. Your guess is right. You just leave it as such. So the last few steps here is we calculate the magnitude of the resultant. We use Pythagoras' theorem, and so by substituting the value for frx, fry, square them, sum them, compute the square root, we find a resultant magnitude of 630.7 newtons. Now, in terms of its position and its direction, we take the arc tangent of Fry over Frx. We do this because we want to make our angle reference with respect to the horizon. And so by substituting the values that we've just previously computed, 621.7 divided by 106.4, take the arctangent of that value, and we end up with a value of 80.3 degrees. Now, we have to fix our free body diagram. Okay, so we have our biceps force vector at 675. That hasn't changed. We have our weight. We label it with the actual value. Okay, so we calculated 19.62. 675 was given to us. And we now draw a vector that reflects our calculation. A vector that's almost the same length. This one actually looks a little bit longer than this one here. I should have drawn this one a little bit shorter here, but we're not going to split hairs at this point. But we give it the label of 630.7 newtons for its magnitude, with an angle from the horizon of 80.3 degrees. Now, this would be the final answer. So when conducting a dynamic analysis, what we've discovered here is that the unknown variables weren't really known on the front end, but by following the systematic approach, we then discovered what the unknown variables were, and that would allow us to continue to solve for those unknown variables and then compute a situation that reflects the external forces that are influencing the kinematic behavior of our system of interest. So this ends our lecture on how to perform a dynamic analysis of a rotating segment.